In the last 5 years, companies have spent over $30 billion on quantum computing R&D. I mean, think about it. Google announced quantum supremacy. IBM published a public roadmap. Microsoft claimed a breakthrough with topological qubits. You'd think we're close to something that actually works, but we're not. And here's the thing. Everyone's celebrating progress, but the real bottleneck, the real challenge that companies are having, the thing that's actually stopping quantum from scaling, isn't really being talked about at all. So it's not the qubits, it's everything else that's around them. So for this video, I want to be very direct about what's happening right now because I am so fascinated by quantum computing. And I've gone down so many rabbit holes with quantum computing, and I want to share with you my thoughts on it. When companies announce a new quantum milestone, such as a new logical qubit, better error rates, say more qubits on a chip, what they're really celebrating, or usually anyways, is one very specific, very narrow problem. It looks impressive in a press release and helps raise money in some cases, or makes investors think they are on an exponential curve. But here's what's actually true. Building a quantum computer isn't about building one really good qubit. It's about building thousands of physical qubits that talk to each other, that are able to stay stable at the same time, and that can correct each other's errors faster than new errors appear. And it's that last part that is where everything breaks. Okay, so the core problem is called error correction overhead. It's not very trendy or sexy, so you don't really hear about it a lot, but it's real and it's enormous. So here's the math for this. Here's what's going on. To get one reliable logical qubit, one qubit you can actually trust to run computation, you need somewhere between 1,000 and 10,000 physical qubits, depending on the architecture. Today, the best systems have a few hundred physical qubits. We're not even close. And those thousands of qubits can't just exist. They have to be monitored, measured, even corrected in real time. Every qubit is decaying. Every measurement introduces error, and every gate operation introduces more error. So the system has to catch and fix those errors faster than the next operation. And that is the challenge or the bottleneck that no one really wants to talk about, because it's not a hardware problem you can just throw money at. It's a systems problem. So here's where I want to be honest about something that I've noticed in this space. Companies will announce a logical qubit breakthrough and it gets covered like it's the turning point. We've seen this over and over again. Those breakthroughs, they do matter a lot, but a lot of times what's actually happening is they've solved one incremental step in a much longer staircase. I'm looking at my staircase. They celebrate it publicly because it's good for fundraising, for investor confidence, for the narrative that quantum is inevitable and imminent. I'm not saying it's dishonest. I'm saying it's incomplete. The small wins, yes, they are real, we need to acknowledge them, but the distance between a lab demo and something that actually runs useful computation is still massive. So here's the thing. Even though the timeline is longer than the hype suggests, this might actually matter right now more than ever, because the infrastructure decisions that are being made today are looking into the future. For example, which error correction code a company bets on, or what qubit architecture they should commit to, how they design the control systems around it. If Google's superconducting approach is the one that scales, quantum computing becomes a hyperscaler story. Only companies with data center scale budgets can afford it. Or say if Microsoft's topological bet wins, the cost curve looks completely different and a different set of companies gets to compete. And if neither wins outright and the field stays a hybrid classical quantum for decades, then NVIDIA and the classical compute layer that's underneath all of this becomes the actual moat. And if you pick the wrong bet, your entire business model becomes obsolete before the tech even matters, which is really high stakes. Let's go through what's actually happening in the labs, because the data here is where you can really see the full picture. So let's start with qubit counts. 5 years ago, IBM had 50 qubits. Remember what I said earlier, you need thousands and thousands of them. Google had similar numbers. Today, IBM has systems with over 1,000 qubits. Google's Willow chip that I'm sure you've heard about, we talk a lot about it, runs 105 qubits, but with meaningfully better error rates. It sounds like large progress or lots of progress. In one sense it is, but here's the catch. More physical qubits doesn't mean more usable power if you can't correct the errors the qubits accumulate. The real metric here isn't physical qubits, it's logical qubits. So in late 2024, Google demonstrated logical qubit error rates for that. It was the first time, and they went down as they added more physical qubits instead of up, which was a huge milestone. But turning that into a large-scale logical processor still requires an overhead ratio in the range of dozens to hundreds of physical qubits per logical qubit, depending on the code that's used. So we still have a long way to go. Now, another company, IBM, they're betting a different error correction approach, a form of quantum LDPC code, which is the claim that they could bring overhead ratio down substantially compared to the surface codes most of the field has relied on, has shown real progress. And it's a big stepping stone. Now, Microsoft, for example, they took a completely different bet. They're pursuing topological qubits, which are theoretically error-resistant by design, meaning they'd need far fewer qubits per logical qubit if the physics holds. Now, one of their big announcements was the Majorana 1 chip back in 2025. I remember everyone was talking about it. They ended up having to retract part of it, I believe, in Nature. So there was still some hype around it though. But Microsoft is betting on physics that works in theory, but hasn't actually been proven in practice. So each of these companies is essentially saying, we don't actually know which physics wins. So we're committing billions of dollars to a different path, which I think is interesting because hopefully one of those paths work versus them all doing the same thing. But it is uncertainty. The fidelity numbers also tell a really similar story. 2-qubit gate fidelity in the best systems is now about 99.5%. 5 years ago, it was closer to 98%. So it's real progress, but to scale error correction reliably, most estimates put the required threshold north of 99.9% consistently. So we're getting closer, but we're still orders of magnitude away from close enough. And there's a piece here too that rarely gets headlines or the spotlight, I find, which is even if the qubit physics is solved, you still need classical control systems fast enough to monitor, decode, correct errors across thousands of qubits in real time. And it's that decoding problem that is an unsolved engineering challenge, which is sitting underneath all of these different architectural bets. So qubit overhead, fidelity thresholds, latency or control latency, decoder complexity, the gap between we have a logical qubit and we have a quantum computer that runs something useful is still years away. Realistically, which pains me to say because I'm so excited about quantum computing, probably decades. So let's zoom out. What does this actually mean? So here's why I spend so much time going into rabbit holes about quantum computing, if you will. The quantum computing industry is real. The progress is real. But we're in a phase where small incremental wins get celebrated like major breakthroughs. And maybe they should, because the narrative is really powerful. Quantum is coming and it will solve everything, or that's how it feels anyways, and break everything. Quantum will probably matter in our lifetime. I'd bet on it. I'm not a bettor, but I would. But it's going to take longer than most people think, likely decades. And I don't think it ever becomes something that the average person interacts with directly. It'll stay infrastructure level, the way most people never have to think about the chips running their cloud services, for example. The companies being cautious about that timeline, investing seriously while still being honest about the bottlenecks and the challenges that they are facing, are the ones playing this smarter long term. Because the real winners won't be the ones who build the first working quantum computer. They'll be whoever understands what quantum computers are actually good for. I mean, drug discovery. I always go to healthcare when I think of it, just the discovery for drugs and solving hopefully cancers and everything like that. But I'll be curious to see who wins this. And that is why this really matters right now, because even with the payoff that's decades out, the decisions, the infrastructure that are being made today really matter. Which companies get to compete and how quantum integrates with classical systems, those decisions already are starting to play out, and we'll see how they play out in the future. So here's my question for you. Do you think quantum computing actually becomes mainstream someday? Or does it stay this infrastructural level, something that powers other systems, but most people never directly interact with, kind of like what I was saying? I'm curious to get your take. I hope some of you push back on my theory on this, because I want to interact with it on a daily basis. I don't know, but we'll see. And then there's the flip side with breaking encryption and security, and what does that look like for our banks, our hospitals, for everything. And there are a lot of cool companies working on that, quantum proofing encryption, but we will see. Time will tell. All right, leave in the comments your thoughts. Do you like these deep dives? Do you want me to do more of them? Leave what videos you love from me. I love going deep on these topics, and I hope you leave these videos feeling smarter and like you maybe learned something that you can take and bring on into your day for someone else who likes quantum computing. All right, I'll see you in the next video. Thank you.